Welcome to Cyclopod, showcasing work by early career geoscientists that is of interest to the cyclostratigraphic community. This podcast is made possible thanks to financial support of the International Subcommission on Timescale Calibration.
Hi there! Welcome to the 12th episode of Cyclopod. This week our guest is Udara Amarathunga from the Australian National University in Canberra. Udara, we're recording this podcast episode not over Zoom, not over Skype, but in person. And that's the first since the start of Cyclopod, and it makes me really happy. We're sitting next to each other in Bergen, Norway, where the paleoceanographic community gathered for the 14th International Conference on Paleoceanography. How is your conference going so far?
Hi David. First, thanks a lot for inviting me to this episode. And yes, Bergen is a really beautiful city and I've fallen in love with the city. And the conference has been a great opportunity for me to meet a lot of people that I've only known through their work. And yes, as finally a PhD student, it's been an important opportunity for me to connect with the worldwide paleoceanographic community. I'm glad that I made it here.
Yeah, and I'm glad that you can present your very important work that you recently published in Nature Geoscience. And that is also the reason why we invited you here to Cyclopod. That work I'm referring to, that deals with the flooding of the Mediterranean some 5.3 million years ago. First of all, many congratulations. It's a very well-written paper that has beautiful figures illustrating the bathymetry and the processes that you are referring to in the manuscript.
Thank you.
So before we dip our toes into the Mediterranean, Udara, I have a somewhat silly question for you. You are originally from Sri Lanka, and so a narrow-minded person might expect you to work on the Asian monsoon or the Indian Ocean paleoceanography, but you're not doing that. You're not doing the obvious thing, and I think that's awesome. What is it that fascinates you about the Mediterranean and the Myo-Pliocene catastrophic environmental changes that you are studying?
Yes, David, you are correct. I spent my whole childhood in Sri Lanka and then I did my bachelor's degree in geology there. But rather than pure geology, I've always been fascinated about the ocean and climate sciences. Unfortunately, there is not enough opportunities for us to pursue a career in these fields of research in Sri Lanka. So that's when I started to find an opportunity elsewhere, and I was lucky enough to find a project that very well suited my research interests. So at ANU in Canberra, at the Climate and Ocean Geosciences group, my project looks at the oceanographic evolution of the Mediterranean and the North African climate from the beginning of the Pliocene to the present. Yes, the Mediterranean fascinates not just me, but a broad community of paleoceanographers. So it fascinates me in three ways. First, the basin is located in the transition zone between the subtropical dry zone and also the temperate westerlies of the southern Europe. And second, the Mediterranean is connected to the global ocean at a very narrow point at Strait of Gibraltar, and it makes the basin a place to study the global ice volume variations. And thirdly, the Mediterranean basin very well records the past landscape changes in northern Africa. So in those three ways, the Mediterranean fascinates me.
It's also fascinating in the past, and I already mentioned the flooding of the Mediterranean 5.3 million years ago. So prior to the flooding, the Mediterranean was largely desiccated, and we observe huge evaporitic deposits all around the Mediterranean when we look into the geological archives from that time. And that's what people call the Messinian salinity crisis. And then, in a very short amount of time, the Mediterranean was filled up by water again. That's the so-called Zanclean flood. Can you give us a little bit more detail on how the Earth looked like back then?
Yes, the world in general over 5 million years ago was way warmer than it is present, and we did not actually have large northern hemispheric ice sheets as we have today. Compared to the present, the sea level was some 20 meters higher and the tectonic configuration was almost similar to present. However, towards the late Miocene, the tectonic shifts at the Strait of Gibraltar resulted in the closure of the Atlantic-Mediterranean gateway. And we know that the Mediterranean basin has a high rate of evaporation compared to the runoff and precipitation. So this results in the drawdown of the basin as the inflow of Atlantic water is restricted. And by some 5.6 million years ago, the Mediterranean reached the peak of its salinity crisis, and it's believed that by this time, the Western basin reached its drawdown to about 1.5 kilometers, and the Eastern basin reached some 2 kilometers. And this is a huge drawdown. So people have been arguing about the termination of the salinity crisis. Some people say that the termination at 5.3 million years was a catastrophic flood that resulted from the collapse of the Gibraltar Seal, and some people say that the Mediterranean was never desiccated actually, so the drawdown was very low and the Atlantic reconnection was a very, very slow process. So we actually still don't have a complete answer to how the Mediterranean was reconnected to the Atlantic, but what we can now do is to study the available records to find an answer.
To answer the questions you just brought up, you are presenting numerical modeling results. And those results, they suggest that it basically took 1 year to fill up the Western Mediterranean. And once that was filled up, it took another year to fill up the Eastern Mediterranean. So the entire Mediterranean Sea filled up with up to 2 kilometers of water in a matter of 2 years. And it did that by means of two waterfalls, one waterfall related to the Gibraltar Strait and another waterfall at Sicily, filling up the Eastern Mediterranean. So tell us a little bit more, how did you do those calculations? That sounds difficult.
This idea of a mega flood was first properly modeled by Daniel Garcia Castellanos, and he presented his results in a paper in Nature in 2009. So it's termed the catastrophic flooding of the Mediterranean, the Zanglean megaflood. So the numerical model uses the erosion of the Seal of Gibraltar, and the idea came up from seismic data that was taken beneath the Strait of Gibraltar. So in the seismic data, what they found was a huge erosive canal across the Seal. And this channel is about 300 kilometers in length and about 14 kilometers wide and 200 meters deep. So in the numerical model, what they did was take an uneroded seal and erode the seal to its present dimensions. So as the seal is eroded, water flows into the basin, and this is a 1.7 kilometer flow, and it's twice as high as the Angel Falls. And imagine how huge it would have been. So as the Western basin is filled, it reaches the Sicily Seal. And when the Sicily Seal is reached, water started flowing into the Eastern Mediterranean. And the drop is even larger than that of the Western basin. And then the Eastern basin fills up.
Yeah, and until the publication of your paper, most people agreed with that model, but they would have assumed that with this super fast flooding of the Mediterranean, normal marine conditions were restored almost overnight, like instantaneously. But your paper challenges that idea, right?
Yes. So the idea of the Messinian salinity crisis came up 5 to 6 decades ago as the people started drilling the Mediterranean. And during these drilling projects, what they found was a very sharp contact at the Miocene-Pliocene boundary. So this big lithologic change made them to depict that the transition from the Messinian salinity crisis towards the Pliocene was an abrupt transition towards normal marine conditions in the Mediterranean. But the evidence we found disproves this idea.
Yeah, indeed. You're saying that in the Western Mediterranean you had normal marine conditions overnight, instantaneously, but it took several thousand years to make the Eastern Mediterranean like a normal marine basin, and in that time between those several thousand years you basically had a saline soup, a hypersaline environment. And one of the lines of evidence that you use to reconstruct that hypersaline environment in the Eastern Mediterranean is the so-called mystery sapropel. Is that correct?
Absolutely.
So can you explain what makes the mystery sapropel different from normal sapropels?
Yes, so first I'll explain briefly what a normal sapropel is. A sapropel is a layer rich in organic matter in the sediment record compared to its surrounding sediments. So, at present, we know that the Mediterranean is very well ventilated due to its active overturning circulation. Because of the well oxygenated water column, all the organic matter produced in the euphotic zone, it gets oxidized before it reaches the basin bottom. So we have mild deposition at the present in the Mediterranean. However, there were past periods of rich organic matter deposition in the Mediterranean basin, which we call as sapropels. So sapropels were formed during the periods of northern hemispheric insolation maximum. So the insolation maximum results in the penetration of African monsoon towards North Africa, and this delivered excess amounts of runoff to the Mediterranean basin. So we know that the density of the fresh water is less compared to the seawater. This less dense water curtailed the deep water formation, and it restricted bottom water ventilation during insolation maximum. As a result, the organic matter that was sinking to the deep basin was preserved, resulting in the formation of sapropels. So we obviously have a sapropel at the Miocene-Pliocene boundary in the eastern Mediterranean, and this actually was discovered during the 1970s when they drilled the eastern basin. They found a sapropel layer deprived of benthic foraminifera. So they could not actually give an explanation to this sapropel, so they named this sapropel the mystery sapropel. So then we use our chronology to look at how long this sapropel took to be deposited. And what we find is this specific sapropel took more than 20,000 years to be deposited. So first it deposits through the earliest Pliocene insolation maxima, and then it runs through the insolation minimum as well. So this is the only Neogene sapropel that was deposited during an insolation minimum. And also it ran across towards the next insolation maxima as well. So it was completed deposition within a period of 26,000 years. So that's what we found.
Yeah, and with a duration of 26,000 years, it is at least 3 times longer than the amount of time that is represented by a normal sapropel. So what is it that caused this long duration? What caused the mystery sapropel to last for so long?
Yeah, so when Daniel did his modeling back in 2009, he looked at what actually happened at the Seal of Gibraltar. He tried to erode this erosive canal and tried to fill the basin and to see how long it would take for the basin to be filled. So what we did was we actually looked at the energy dynamics within the basin. So what we used the energy of the flow to compute how the basin will behave as the waterfall fills the Mediterranean. So we find that the flow is so energetic that it could mix with the Messinian brines of the basin. So during the Messinian salinity crisis, the basin was filled with about 2 kilometers thick brine bodies, and these brines were at least of gypsum saturation, which should have been very, very dense. So the release of energy at the peak of the flooding event, we find that in a single day, it was more than 500 times the annual dissipation of energy at the Niagara Falls, which is a huge amount of energy. So this energy could mix those dense brines with the incoming Atlantic waters. And as the western basin filled towards the Sicily Seal, the basin was fully mixed with these less saline brines. And then as the eastern basin was filled up, all the salt in the western basin was transferred into the eastern basin. So finally, we end up with a normal basin in the western Mediterranean, whereas the eastern basin is filled up with the Messinian salts. So that made the eastern basin to be stratified at the Sicily Seal level, according to our model.
Yeah, and long stratification, or 26,000 years of stratification, means 26,000 years of sapropel-like deposition, and that is what you neatly illustrate in your paper.
Yes, so now we know that Mediterranean has normal marine conditions. So all the salt that was in the eastern basin must have been transported to the Atlantic basin, and this happened by turbulent diffusion. So we use basic physical oceanographic ideas to compute how long it would take to remove all the salt to the Atlantic. What we find is it would have taken from 10,000 to 40,000 years to remove all the salt back to the Atlantic. So this agrees very well with our chronology, which tells that the mystery sapropel should have been about 26,000 years of deposition of organic matter.
Now it's time for the number of the month. And this month the number is 1920. Recently I learned that in the 1920s there was the idea to build a dam on Gibraltar, on the Strait of Gibraltar, to gain land, to dry out the Mediterranean. With your research in mind, why do you think this would have been a terribly, terribly bad idea?
Yes, so there was this idea about building a huge dam across the Seal of Gibraltar, and this was called the Atlantropa project. So their idea was to provide electricity to the region, and this idea never came a reality, and actually the engineer who proposed the project passed away without realizing his ideas. So in my view, a dam would have drawn down the basin by a few hundred of meters, and this would have resulted in huge salt pans along the margins of the Mediterranean basin. So we would not have been able to grow any crops in the region, and it won't be a suitable place for people to settle. And imagine if the dam were to break, maybe due to a war, it would have been catastrophic, killing all the people. So certainly I think it was not a good idea.
To end this podcast, Udara, I would like to ask you about another hypothesis that is sometimes cited when we talk about the end of the Messinian salinity crisis. So some people claim that the level of the Mediterranean during the Messinian salinity crisis was not so much lower than we now think it is. Those people claim it's only a few hundred meters lower than the Atlantic level and not a few thousands as we currently think. And under this scenario, to re-establish the connection between the Atlantic and the Mediterranean Sea, these people think that the water would have come over the Parathetis connection, and so the Mediterranean would not have been filling from the Atlantic side, but through the Parathetis connection, and therefore it would be a much more gradual process. The Mediterranean would fill gradually, and therefore the connection to the Atlantic would be established only later and gradually. Why do you think this hypothesis is no longer viable?
Yes, as I stated earlier, even after 50 years of research, all these topics are still debated, and there's a group of scientists that believe that the Mediterranean base level was higher than we think. So the question is, we know exactly that during the peak of the salinity crisis, gypsum and halite was deposited in the deep basin, and this must have resulted in thick brine columns according to our view. And the question is, where did all the salt go after the salinity crisis? So if the salts stayed in the western basin as we interpret as also in the eastern basin, the western basin also must have been stratified during a gradual reconnection, and we should see a sapropel deposited at the western basin as well, but we don't see that now. We only see a sapropel in the eastern basin. That's why we propose that all the salt in the western basin was transferred to the eastern basin across the Sicily Seal. So that's our view of the problem, but certainly this is still open to debate.
Thank you, Udara, for the nice chat and for the very compelling arguments you made defending the hypothesis that the Mediterranean filled up in a matter of 2 years after the Gibraltar sill was eroded, and about the salt transfer from the Western Mediterranean into the Eastern Mediterranean, taking about 26,000 years to re-establish normal marine conditions in the Eastern Mediterranean. Really fascinating results, and I think it's really cool that Udara's work spans all the relevant timescales to understand the end of the Messinian salinity crisis. We talked about the 2 years to reflood the Mediterranean Sea, but also the 26,000 years to restore normal conditions. I really like scientific work that spans this wide range of timescales. Udara, thank you very much for the interview. And at this point, I would also like to thank our audience for listening to this 12th episode of Cyclopod. See you next time.